Transmission characteristics of chiral nanostructures embedded waveguides. Good morning. My name is Adityatripathi. I am a student of Dr. Sunil Kumar from the Physics Department, IIT Delhi. This is the outline of my presentation. I'll be dealing with the objectives and literature review, computational techniques and procedures, results and inferences, summary, and future scope. Now, the objective of this research was to study the effect of surface plasmon fields in such a chirooptical system and find out if or not this system has any applications. And then the second objective was to study the polarization sensitive transmission characteristics of these waveguides. Now, the chiral nanostructures are embedded on these planar waveguides, as you can see in this figure. This figure over here has these brown chiral helices, which have the same material as the core of this planar waveguide, and on top of these helical nanostructures we have metal nanoparticles, which are essentially made of gold. Now, we expect that the transmission as well as the scattering will be highly geometry dependent. The upper cladding layer is kept thin to ensure that we have total internal evanescent waves, as well as since the material of the core and the helix or the helical nanostructures is the same, we must see some frustrated total internal reflection, and as a result some of the light must go inside these helical nanostructures. Sort of situation where helical nanostructures would act as a sub-waveguide structure. I'll come back to this point later. This is how people have made these substrates. These are how they look in reality. And we expect that there must be some Bragg diffractive lines in these lattices, and adding plasmonic nanoparticles has to some extent indeed enhanced this effect. Now, we will try to investigate the scattering due to these metal nanoparticles, the plasmon enhanced scattering, and try to find out its wavelength dependence and how it affects the transmission. To do this, we have simulated the extinction cross-section and scattering cross-section plots, which arise due to surface plasmon effects in the lattice. Yeah, indeed. There is one point which is important. There are two lattices. One is the lattice of the helical nanostructures, on top of which we have a lattice of metal nanoparticles. Yeah, so the computational techniques which we use are finite dimensional vector beam propagational method, and then a coupled dipole approach, which is also known as the discrete dipole approximation. The finite the BPM will give us the electric field at the sites of the nanoparticles, at the lattice points which contain the nanoparticles. And then, since after we have got the incident electric field on the nanoparticle, we can easily calculate extinction, scattering, and in fact the dipole moments of individual nanoparticles using the coupled dipole model. For the simulations, this is how we'll go about this. We treat the helical nanostructure array as our metamaterial, we discretize it, and then we discretize the entire structure, even the waveguide as well as the helical nanostructure array. And then we assume that the gold nanoparticles are present only at one lattice point, which is at the top of the helix, or in fact only one lattice point in the metamaterial. I mean, I hope I am making myself clear. Now and after we have done this, we apply the beam propagation method to find out the electric field at these lattice points where the gold nanoparticles are present, and then we apply the coupled dipole model to find out the plasmon effect. These are our results. This is for the Y incident polarization. We have the extinction cross section against the wavelength. Now we have compared our structure with a plane wave excitation, which would have excited the same lattice of nanoparticles had there been no chiral geometry, nothing else. I hope I make myself clear this time. So the plane wave excitation where there is no chiral geometry, and in the blue line, and in the red line we have the extinction for the helical nanostructures, which is our sample. So now we can see one thing very clearly. The 506.9 nanometers line, which is this one over here, this represents the single particle resonance. Now this is indeed sharper and somewhat larger for the plane wave excitation. This has become broader and shorter for our substrate. However, the lattice modes or the additional modes which arise due to the diffractive coupling were broad for the plane wave excitation. You can see these ones. This is somewhere around 428, and this is somewhere around 600. So these have become sharper for the helical nanostructures, and they were broader for our plane wave excitation. Now for the X polarization of the incident light, please note the polarizations are defined with respect to the diagram the diagram of the substrate. I mean the diagram of our of these waveguides, the nanostructure embedded waveguides, which is shown earlier. Now coming back to the X polarization, we have the same nomenclature. The only difference is that the polarization of the incident light is different. Here there is another interesting aspect. Here the difference between the difference between the single particle resonance is very less. The single particle peak is not so distinguishable for the helical nanostructures and the plane wave excitation. However, we find another mode here at around 550 nanometers. This is again due to some sort of diffractive coupling, but then this is kind of a surprise for us. I mean, we are not expecting this to happen because none of the lattice constants is in itself 550 nanometers. Now coming back to the now I consider the case of circularly polarized input or circularly polarized excitation. The thing with this is that this circularly polarized excitation is not giving us anything different, because both the left and the right circularly polarized light give us the same output. I mean the same extinction cross-section plot. So we have avoided the usage of the term left or right. And secondly, we don't find any prominent effect apart from this single particle plasmonic resonance line. There are no modes. However, there is one over here, but this is very weak to be considered into account. Yeah, coming back to our scattering plots. This is the comparison of the scattering cross section for our three excitations. One is the X polarized, Y polarized, and the circularly polarized cases. Here we can clearly see that in the Y polarized case we have um, an excitation peak occurring at 600 nanometers. I mean, yeah, scattering peaks up at 600 nanometers. Indeed, that happens to be one of the modes as well for this arrangement of nanoparticles. But then there is also something happening at 550 nanometers. I mean, this also seems to me like a peak. However, this peak is not clearly evident because of the presence of the single particle peak very close by. So these are somewhat indistinguishable. And another important finding was that this 428 nanometer peak over here becomes highly sharpened, but then in the scattering cross-section plot we don't find anything happening in this 428 nanometers region. This is something new, something strange. Now coming back to the now I present my inferences. The single nanoparticle peak at 506.9 nanometers is almost unaffected by the polarization of incident light, which is true, and it is obvious because this peak this peak is independent of phase. This peak is the fundamental mode which you will always get in any case. It is independent of the phase of the nanoparticle which is oscillating, or which has the LSPR resonance. The plasmonic modes arising due to now only the modes which arise due to diffractive coupling are dependent on the phase geometry relationship. One example I have for the for the one-dimensional array of nanoparticles, let's say 3 nanoparticles over here, placed in a straight line. Now you excite it perpendicular to the plane in which they are contained. Now you find that different modes are here which depend on the nanoparticle separation, which is a geometry parameter. So indeed, the phase between we can say the phase between adjacent nanoparticles, or let's say any two nanoparticles, is dependent on their relative geometry and the wavelength of the incident excitation, which is not the case for the single nanoparticle peak. This gives us the other modes. The single nanoparticle peak, you can see the single nanoparticle mode. These ones, these are always there. But since the now 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 this is we are getting these modes, this 550 nanometers, this 428 nanometers, 600 nanometers, all sharp and prominent. This is because the exciting light, the excitation wavelength, due to total internal reflection, gets into these helical nanostructures, and the phase they accumulate in these helical nanostructures is highly complicated. This is just not just uh, it is not just two nanoparticles separated by some distance from each other. The phase will be given. The total phase is given by this complicated expression, and hence um, they present to us some strange phenomena. And the extinction and scattering cross sections for the left and the right circularly polarized excitations were the same. This is because both the polarizations would see this two-dimensional lattice of metal nanoparticles as the same. They won't find any difference when coming to this when they reach the layer of the metal nanoparticles. This can be easily verified once we are able to calculate this phase integral phi. You can easily find that the phases for the left and the right circularly polarized light will closely match. Now, the additional peaks, apart from the 506.9 nanometers, which occur at 550 and 600 nanometers, and another one at 428 nanometers. So, these peaks are really sharp, and these are somewhat different from the spacing between compared to the spacing between the nanoparticles. This is simply because of the fact that the helix would also act as a waveguide, and the light would travel here, 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 here. This due to frustrated total internal reflection from the upper cladding, and the incident polarization can be X or Y, let's say. Now, we all remember that that the modes of the waveguide are also polarization dependent. Yeah, those TE and TM modes. Here, due to the polarization difference, um, the propagation constants in the helical nanostructure would be different for both the X and Y polarizations, and hence the incident electric field accumulates some different phases as as they reach the gold nanoparticles. So the gold nanoparticle has a different incident electric field for X and Y polarizations respectively, and hence since they have accumulated phase differently, we get the additional modes at different wavelengths. Now this setup can also be used as a plasmonic frequency selector, which is somewhat like a litro-mounted prism or a Fabry-Perot etalon, which selects the resonating wavelength inside a helium-neon laser cavity. You can see this from the figure. The specific laser wavelength um, which we want to laser at is selected by the litroprism. Yeah. So here we tune the polarization between X and Y polarization. We have somewhat shifted our plasmonic mode from 550 nanometers to 600 nanometers. Now this is a great degree of tunability and control, which is again very interesting. Now to summarize this research, I would say that indeed we find that the far field scattering is strongly polarization sensitive, and this can be exploited for device applications. The single nanoparticle peak at 506.9 nanometers is almost unaffected by simply changing the polarization of exciting radiation. The additional plasmonic mode is shifted from 550 to 600 nanometers. This can also be used for analyzing optical properties of DNA and making broadband circular polarizers and sensing applications. We are also summarizing our results and putting in a few more to so that we can prepare. We are in process of preparing our manuscript for submitting to, let's say, some journal. So this is pretty much it, and this is the appendix. This contains all the formulae for the coupled dipole model, the coupled dipole approach. This is how we calculate the dipole moments of the individual nanoparticles, and then this is the formula for use for calculating the extinction cross section. Thank you.